Hello, and welcome to a digital statistics lecture for Salt Lake Community College. In this video, we're going to be talking about section 11.1, inference about two proportion populations, or two population proportions, rather. What we have done up to this point is talk about how to do hypothesis testing and how to do confidence intervals on one population proportion. However, we're also going to have instances where when we take a sample, we have two different groups we will want to compare. And the main point will be to try to show that there is a similarity or difference between those two groups. That will lead us to what we have here, which is two population proportions, trying to see if there's a difference between two identified groups of values. We say that the sampling method to gather those groups are independent when the individuals in one of the sample groups does not dictate which individuals will be in the second sample. We call it dependent if that does dictate the individuals that are in the second example. And we sometimes call that a matched pairs design. So if the two groups that we select are intimately related, or there's an actual reason why one group is in the or one group is selected compared to the other group, we call that matched pairs, we call that dependent. Now, this isn't really an issue as much where we usually wanted to say if they're independent, because here we're talking about them being independent of each other. We are not really saying that they're either independent or dependent on the population, we're saying if they're independent or dependent from each other. For example, we have here Joliet Junior College decided to implement a course redesign of its developmental math program. Students either enrolled in traditional lecture format course or a lab-based format in which lectures and homework are done using video in the course management system MyMathLab. Should sound kind of funny to go through. There were 1,200 students enrolled in the traditional lecture format and 300 enrolled in the lab-based format. The goal of the study was to determine whether the proportion of students who passed the lab-based format exceeded that of the lecture format. So what we're doing is we gathered two groups, one in traditional, one in lab-based, and we're seeing if there's a difference in the overall grade earned by those two, or at least the proportion of those that passed. However, in this case, notice that we have 1,200 students enrolled in traditional and 300 enrolled in the lab-based formats. This is not an issue that those are two different values. However, what we do want to talk about is if there is actual paired design between them. I do not see any relation saying that maybe the students in the traditional course is friends with somebody in the lab-based format, or we're working with their brother or somebody they went to high school, some connection between the two. Because there is no intimate connection between them, we say that they are independent of each other. So the sampling method is independent because individuals in lecture-based format are not related to the individuals in the lab-based formats in some way. As a comparison, we have, do women tend to select a spouse who has an IQ higher than their own? To answer this question, researchers randomly selected 20 women and their husbands. So we have 20 women and we have 20 men. They measured the IQ of each husband-wife team to determine if there's a significant difference in IQ. So this would be an example where we're comparing means. We're comparing the average IQ for the women, average IQ for the men, and trying to see if there's a significant difference between the two. However, these two groups are dependent on each other. There is an intimate connection between the two. They are related in some way. So they have been dependently selected. Alright, so again, independent and dependent in that context is not really an issue that we need to address. It's just something that we need to keep in mind to think about how the samples were selected. Now, what we're going to do is talk about how we do hypothesis testing and also confidence intervals on these. To do so, we need to talk about the different conditions that we need to meet. The three conditions are going to be the same. The samples that we gather are from a simple random sample, so we still want that. We also want NP 1 minus P greater than or equal to 10, but we want that for both sample 1, hence the subscript of 1 there, and sample 2, hence the subscript of 2 there. So we're going to have to do this for both groups. Likewise, we're also going to make sure that both groups are less than 5% of the population. So we want to make sure that all our conditions are true for all groups that we're selecting. Notice, however, in this case, compared to previous cases where we had NP 1 minus P greater than or equal to 10, where technically we were using P sub 0, the value from our null hypothesis. In this case, we're using P hat, which means we're using the sample proportion. This is the only time that we will be doing this, where we will be using the sample proportion in our checks for normality. If we were doing just one proportion, we would do the proportion that would be in our hypothesis. Again, make sure you keep that in mind. Okay, so essentially we're going to do all our requirements for both groups here. When we have those requirements set up, then we'll go through our hypothesis testing. We'll either have two-tailed, left-tailed, or right-tailed, so the direction will still indicate the sign that we use, either not equal to, less than, or greater than. However, here the hypotheses that we have set up are going to be comparing the two proportions. And we're going to usually keep it with these symbols. We're actually not going to put in values here. Very often we'll keep it p sub 1 equal to p sub 2 and p sub 1 not equal to p sub 2. Or we'll maybe put in our own subscripts. Like in the previous case for husbands and wives, maybe we'll do proportion sub women equals proportion sub men, saying that there is no difference between the proportion for women and men. However, we're not really going to have values in those hypothesis testing. Then we'll calculate z sub 0, which we could do by hand or in our calculator, which we're going to use with 2-prop z test, and get our p-value. Notice that when we did one proportion, we were doing 1-prop z test for hypothesis testing. Now for two proportions, all that changes is that little number right there, since we're doing two proportions. Otherwise, the process is going to be the same. We still compare to alpha. If it is less than alpha, we reject. If it is greater than alpha, we fail to reject. So we still have the same overall conclusions. All right, a couple examples of this then. All right, researchers at Harris Interactive wondered if there is a difference between males and females in regard to some common annoyances. They asked a random survey of males and females the following question. Are you annoyed by people who repeatedly check their mobile phones while having an in-person conversation? Among 540 males surveyed, 178 responded yes. And among the 560 females surveyed, 206 recorded yes. Does the evidence suggest a higher proportion of females are annoyed by this behavior? Conduct the appropriate test using alpha 0.05 level significance. All right, so we're going to have to check our requirements. Notice we have a lot more room here because it does tend to take a little while. All right, so for randomness, it says random. So it does say random in the description of the problem. It says that they asked a random survey of males and females. So random survey. So it does say random. All right. For our second condition, we're going to check NP1 minus P, but we're going to do so for both groups. We want to make sure that they're both greater than or equal to 10. I'll say men. We have 540 men responding. And what we're going to need to do is multiply that by the proportion. That proportion is the 178 out of 540, so we'll find that. P sub hat for men is 178 out of 540. And while we're at it, we can also find the same thing for women. So P hat for women, because we're going to need that in just a moment. That'll be 206 out of 560. And we could just round these to 2 decimal places to make it easier for us. So on our calculator here, we could type in 178 divided by 540, and also 206 divided by 560. We get 33% and 37% approximately. So 0.33 and 0.37. All right, so for men, we have 0.33 times 1 minus 0.33. All right, and we're going to find out what that is and compare. All right, So we'll calculate that in just a second. We're also going to do the same thing for women. Where we have 560 total women times 0.37 times 1 minus 0.37. Let's calculate both of these. All right, for men, we have 540 times 0.33 times 1 minus 0.33. We get 119, which is definitely above 10, so we're good. And for women, we have 560 times 0.37 times 1 minus 0.37. That gives us 130. So 119 and 130. 130 is greater than or equal to 10, so we're good for women. And for men, we have 119, which is also greater than or equal to 10. So we're good there. All right, that's our second requirement. It takes a little bit longer, but that's just because we have to check two groups. So it's like doing two problems here. All right, for men, we're also going to talk about how many men we have recorded. So we have 540 men responding, and we're looking at just men and women in general. It doesn't say what population. So we could say something like 540 men. I'll type this out to make it a little bit cleaner. What we want to say is something along the lines of 540 men is likely less than 5% of all men. It's a good way to address that. So we can say 540 men is likely less than 5% of all men. And also we could say 560 women is likely less than 5% of all women. All right, so just move that up a bit. With all those conditions down, then that means that we are good. We have verified normality, at least to the extent that we need. So we have random, we have both samples are large enough, and we also have that they are small enough compared to the population. So everything seems good. With that, we should be able to run through and calculate our hypotheses. For our hypotheses, what we can do is just set up P sub men and P sub men. I like to do subscripts, and since we're just doing men and women, M and W are pretty obvious. And for the null hypothesis, it's still going to be the same, where we set up the null hypothesis to be equal to each other. This is saying that the proportion for men is equal to the proportion for women. The question is asking, does the evidence suggest a higher proportion of females are annoyed by this behavior? So what we're trying to see is if the proportion of females or the proportion of women is higher. So our symbol should be like this, indicating the proportion of women is higher. This is how I typically do it. However, it can be done in another way. Some like to do it with P sub 1 and P sub 2. So they'll set up the null as P sub 1 equals P sub 2. And then P sub 1 less than P sub 2. If you do that, though, you have to define on the side what P sub 1 equals. So P sub 1 is for men, and P sub 2 is for women. So this would be the first method that you could do this. This would be the second method you could do this. So either one would work. I like to do this one, particularly if they're pretty obvious to do with subscripts. So a little bit easier. Now that we have those in, we can determine the p-value. To do so, what we're going to do is work with, again, 2-prop z-test. 2-prop because we're doing two proportions, z because the test statistic is based on the z-score, and test because we're doing a hypothesis test. That is going to be located in the same place as our hypothesis testing was before, so stat in test, and what we want is 2-prop z-test, so we want number 6 right there. Well, you open up 6, it'll ask us for a few things. It'll ask us for x1, n1, x2, and n2, and then the direction. So x1 is going to be my first, or my value for my first proportion, and n1 is going to be my sample size for my first proportion. Okay. So with these two values, these are the values that we use to make our first fraction. If I scroll up a bit, the first fraction we made for men was up in the top corner here. We have 178 out of 540. So 178 out of 540, and then for women we have 206 out of 560. So x1 is 178, n1 is 540. So that's going to be the proportion for men. x2 and n2 are going to define the proportions for women. So x2 is 206 out of the total for n2, which is 560. And the direction that we use in our hypothesis test was less than. So we have p sub 1, which is for men, is less than p sub 2, which was for women. So there is a benefit then for doing the second method, because then it'll align a little bit easier with your testing. However, it shouldn't really matter. So it's up to you, whichever one you want to do. We run through that, 178, 540, 206, and 560, and we make sure we do less than. We can calculate, and we get our z-score, our test statistic, of negative 1.329, or negative 1.33. So a little bit more than 1 standard deviation away. And we get a p-value of 0.0918. The other values we get here, p sub 1, that's proportion for 1, which we calculated earlier, was 0.33. Proportion 2, we calculated earlier, was 0.77. And p hat itself is kind of the average between the two. Then n1 and n2 are just sample sizes yet again. Now, in the description, we had a value to use for alpha for comparison purposes. We had alpha is 0.05, so that's what we're going to use. Since we have alpha is 0.05, we can then say that p is greater than alpha, which means that we failed to reject the null hypothesis. We did not get enough information. There is insufficient evidence to claim that, let's see how to word this, to claim that the proportion of men, or the proportion of women is higher than the proportion for men. Because that's how the original description put it. They wanted to see if the proportion of women was higher. And it's about the behavior of texting. So if the proportion of women who get annoyed by texting while having a conversation is higher than the proportion of men. So you can put more context into it, but this should suffice. All right, so that's good for our hypothesis test, and we are done. Notice that this follows the exact same tenets as our previous hypothesis testing. That's kind of the point here. We're only just doing 2 proportions now, which just changes the program a little bit. We're still going to set up the stuff and knock it down the same way. All right. Another one, we have researchers at Harris Interactive wonder if there's a difference between males and females in regard to whether they typically buy name brand or store brand products. They asked a random sample of men and women the following question, and according to 1,104 men surveyed, 343 indicated they buy name brand over store brand drugs. And among the 1,172 females surveyed, 295 indicated they buy name brand over store brand. Does evidence suggest a lower proportion of females buy name brand over store brand drugs? Conduct the appropriate tests under alpha 0.05. Okay, so we're going to check our requirements, and to do so, we're going to find both of our proportions. So proportion for males, which is given first, was 343 out of 1,104. And the proportion for females, so I guess I'll use F here just to keep with the wording that they use. So the proportion for females is 295 out of 1172. All right. We want to find what both of these, and we can round them to 2 decimal places because it shouldn't really matter. If you recall, in the last case, we had a little bit over 500, and those were big enough. We still want to confirm here. So 343 divided by 1104, and 295 divided by 1172. What we get here is about 31 and 25%. So 0.31 for males and 0.25 for females. All right, now for our requirements. Let's see here. We want first to check randomness. If I look into my description, they asked a random sample of males and females. So it says random, we're good. That's all we're looking for. All right. Then for our second condition, we have for males, we have our sample size, 1104, times the sample proportion of 0.31, times 1 minus 0.31. We're going to find that. And we're also going to do the same thing for females, where they have 1172 times 0.25 times 1 minus 0.25. So you need to find what both of these are. All right, so for males, we have 1104 times 0.31 times 1 minus 0.31. And for women, we have 1172 times 0.25 times 1 minus 0.25. Over here, then, we get, for males, we got 236, which is greater than or equal to 10. So that's good. And then for women, we have 219, which technically rounds to 220, but it doesn't really matter. It's a number that's greater than or equal to 10. That's all we need. Then we just need to make a condition talking about the percentage, or making sure that it's less than 5% of the population. So it doesn't say where the females and men come from, like what country or what type of people they are. They're just males and females. So since it's so broad, we can very easily claim that 1,104 males is likely less than 5% of all males, and that also 1172 females is likely less than 5% of all females. All right. Some statement like that addresses both the sample size of men and also women. With that, we should be done with our conditions, so we should be able to move on and put everything together. Let me just move that right there. There we go. Okay. So all our conditions are in place. All right. Now for our hypothesis testing. I'm going to use my subscripts of M and F again. So erase that. So I'm going to set up my proportions with both of those values in mind. So proportion of males for a null hypothesis is that they should be equal to the proportion for females. And then for my alternative, I have proportion of males and the proportion of females. And what we're looking for is that the proportion of females is lower than the proportion of males, according to the description, seeing if they are less likely to buy name brand over store brand drugs. All right. To calculate my p-value, I can set up with 2-prop z-test yet again. Using my values that we had in my description earlier. So x1 was for men was 343 out of the total sample for men, which was 1104. I can see it there on my calculator still. And then for women, there were 295 women out of the total of 1172. And what we're looking for is, based on my alternative hypothesis, if P1 is greater than P2. With that, we should be able to find Z and P and compare that to alpha, which was given in the description to be 0.05. All right. With all that, we can run that. Again, go into test, and we're looking for 2-prop Z test, which should be the 6th option. Plug in our values appropriately, so 343, 1104, 295, 1172, and we want greater than. Run that, we get Z is 3.13 approximately. And we get p-value of 8.71, but notice that there's scientific notation at the end of that. So 8.71 e -4, which means 0.000871. That is incredibly small, and we get definitely that p is less than alpha. So because the p-value is smaller than alpha, that means we have enough information, we are safe to reject the null hypothesis and say that there is enough evidence, or there's sufficient evidence to claim that the proportion of females who buy name brand over store brand is less than the proportion of men or males that buy name brand over store brand. Something like that. All right. So that covers yet another example of a hypothesis test. Now, hypothesis testing is not the only thing we can do with 2 proportions. What we can also do is find a confidence interval for 2 proportions. And technically, the test statistic that we'll use, or sorry, not the test statistic, the prior estimates, or p sub 0, what we would typically have here, the original value, is going to be the difference between the 2 proportions. If they're equal, then we're kind of assuming that the difference is 0. And then we're trying to show that's either below it or above it in some way. So we have kind of complicated looking formulas for both the lower bound and upper bound for a confidence interval. And we'll talk about those in just a moment. But in order to create a confidence interval, we need to do our checks. And we have the same 3 checks we've always had. Simple random sample, np1 minus p greater than or equal to 10, and we want to make sure that they're independent. Once we have those and set up our confidence intervals, then we can interpret this. And again, I'm going to interpret it the way that I did in Chapter 9, saying that you are % confident that the interval will contain the value you're looking for, which the value that we're looking for is the difference in proportions. In order to do this, we do have a calculator function available to us, and that function is going to be 2prop z int. Again, recall from Chapter 9, when we were doing proportions for confidence intervals, we had 1prop z int. Just like in 10, we had 1prop z test. The only thing changing now is the fact that we're dealing with 2 proportions. So now we are dealing with 2prop z int. All right, a couple examples of this. In the Sullivan Statistics Survey, 695 out of 1,000 randomly selected males had a Facebook account, and 845 of 1,000 randomly selected females had Facebook accounts. So we have our values presented there for both males and females. Construct a 90% confidence interval, so that's our level of confidence, for the difference between proportions, P male minus P female. That direction is very important. Use the interval to determine if females are at least 10% more likely to have a Facebook account. All right, so first our conditions, we should address those. Doesn't really give us space, so I'll just type them out here. We have random, so we're good with that. We have 1,000 men and 1,000 women that have a Facebook account. That's definitely less than 5% of all men and women that have a Facebook account, so we're good with the independence condition. And also, if we check 695 out of 1,000, which is 0.695, and we use that with NP times 1 minus P, so 1,000 times 0.695 times 1 minus 0.695. What we get is 211. That's more than 10, so we're good there. Likewise, for women, 845 out of 1,000 is 0.845. So 845 times 1,000, our sample size for women, times the proportion of women, which is 845, times 1 minus 0.845, is also definitely going to be more than 10. So not nearly as much, but still more than 10. So all the conditions are okay. We can assume that this is normal. To construct this confidence interval, we're going to run with 2prop z int. And the values that we plug in are basically the same as the values we did for 2prop z test. So it's going to ask us for x1 and n1. x1 and n1 are going to be p male according to this direction here. That's going to be x1, that's going to be x2. So, well, I'll just say 1. That's 1, and that is 2. For x1 and n1, we have 695 men out of 1,000 women. And for x2 and n2, for women, we have 845 women out of 1,000 women. And then it's also going to ask us for the C level, which here is 0.90. I believe that's it. So, stats, over to 2prop z int. 2prop z int is kind of low there. I think it's on B here. Yep. So we want B, 2prop z int. And yep, those are the only values they asked for. So 695, 1,000, 845, and 1,000, and 0.90. We calculate, we get our interval. We get negative 0.1805. Don't worry about it being negative. That actually is typical. And negative 0.1195. So that would be our confidence interval. So they are negative, and some people would look at that and say, oh, that's weird, you shouldn't have negative proportions. However, the reason we have a negative proportion is because what we're analyzing is the P sub male minus P sub female. If the proportion in the confidence interval ends up being positive, what that means was the P male was larger than P female. If the proportion is negative, that means the P female was larger than the P male. And even from what we saw earlier, yeah, the proportion of men is smaller than the proportion of women, so this direction is going to be negative. So this is expected. And it says, use the interval to determine if females are at least 10% more likely to have a Facebook account. Well, if they're at least 10% more likely, that means 10% or more. And based on this interval, yeah, I'd say that they are likely more, at least 10% more likely to have a Facebook account, because this is 11.95%, this is 18.05%. We're believing that the difference of proportions is somewhere within that interval, and that is much more than 10%, so everything seems good. We'd say that there's a 9% confidence that the difference of proportions is in the interval right there, so I'll just forgo writing it one more time. And we can conclude that women are at least 10% more likely to have a Facebook account than men. All right. Now, I will again say that I don't like this interpretation order. I will say that you are 90% confident that this interval up here contains the true difference of proportions for men and women. So, I am a certain percent likely about that interval because I made that interval. I should be confident about that thing that I made, not the difference of proportions, which is an unknown parameter. All right, one more question to go through this. Again, if you have not already, please pause and try this question on your own first, and then unpause and see how you did. The body mass index of an individual is a measure used to judge whether an individual is overweight or not. A BMI between 20 and 25 indicates a normal weight. In a survey of 750 men and 750 women, so our sample size for men, our sample size for women, they're equal, that's neat. The Gallup organization found that 270 women and 203 men were normal weight. Weird that those are put in reverse order now. Construct a 90% confidence interval to gauge whether there's a difference in the proportion of men and women who are normal weight. Then interpret the interval. Okay. Again, we should address conditions before we go into this. For normality, first we want to check randomness. It doesn't exactly say random, but what it does say is survey. That's about as good as we got. So we're going to say something along the lines of, as long as that survey was conducted randomly. For the independence criterion, the 750 men, 750 women, says that they didn't come from a specific group. They're just men and women. So that's likely less than 5% of all men and women that exist. So we're good there. And then our proportions. For women, we have 270 out of 750. For men, we have 203 out of 750. And we should need to check both of those. So 750 times for women was 0.36 times 1 minus 0.36 to see if this is bigger than 10. And it is by quite a bit, so we're good there. And then for men, we have 750 times 0.27 about times 1 minus 0.27. And we have 147. That's also more than 10, so we're good. All the conditions are met. We have normality. We can work through this. For our confidence interval then, what we have is two prop rather. Z int for confidence interval. For x1 and n1, as well as x2 and n2, we have to put in our proportions. It's not really going to matter what we do for n2 and n1 because they're both 750, but it does matter for x1 and x2. We want a 90% confidence interval to gauge whether there's a difference between the proportion of men and women who are normal weight. So I'm going to say then that this first group is for men, and that this second group is for women. You can reverse this and still analyze the interval correct way. This one just doesn't give us a specific direction. So for x1 and n1, for men, we have 203 men out of 750. And we have 270 women out of 750. Based on these proportions, looks like I'm going to get a negative confidence interval because this 203 out of 750 is less than 270 out of 750. So that seems about right that we'll get something less than 0 here. Confidence interval or confidence level is 0.90 as given in the description. And then we can find our interval. So stats, tests, we run 6, or not 6, B rather. B for 2prop Z int. X1 is 203 out of 750, X2 is 270 out of 750, and then 0.90 yet again. We calculate, and we get an interval from negative 0.1286 up to negative 0.05. Notice that that interval is entirely negative. It does not include the value of 0. What that means is that it's more likely that there is a difference between the proportion of women and men. If 0 is included, which would be a null difference between the two, as difference of 0, then that would imply that it is still possible that there is no difference between these two. However, because 0 is not included, there does seem to be a difference. So there's a 9% confidence interval that 9% confidence that the difference of proportions is in the interval right here, and we can conclude that in this case, women are more likely to have a normal weight than men. Or you could say we can conclude that men are less likely to have a normal weight than women. Either way would imply the same thing. We can imply this direction because looking at this interval, this is, again, as I said, all negative is not including 0. So it does imply that there is a difference between the two. If 0 was included, like if I did a 95% confidence interval, just as an example. So if I go back here, do stat test, and I run it on a 95% confidence interval, I do the exact same stuff, but just change it to 95, which should change the interval to be wider, as we know. I get an interval that goes from negative 0.1361 up to negative 0.0425. Still doesn't include 0, so it still would imply a difference. However, if I did have an interval that was wide enough that it did include 0, then I would be a little bit skeptical. Alright, so that's it for both hypothesis testing and confidence intervals on two proportions. At this point, I recommend going through the homework for section 11.1, trying that on your own, and seeing how you do. I hope this helped, and I hope you have a wonderful day.